Okay, now that we have all these different series and different ways of determining whether or not a series will converge or diverge, and we need to ask that question and answer the question of, does the series converge or diverge? We have to know when should we use each one. So this is a general approach that we should use in going through a lot of these questions. This should be your thought process that you use as you look at each one now. You know, as we've been going through, it's been a little bit easier because when we do the integral test, all the problems that I assign in the homework are integral test questions. Then as I do another one, same thing. But now they're all going to be mixed together. And so you have to know, when should I use which particular test, and which one should I use first, which one should I use second. So this is a good overview of what you should be looking at. So first thing, always look to see if the nth term test applies. Okay? Does the nth term approach 0? If it doesn't approach 0, remember, if you take the limit as n goes to infinity of the terms themselves and they don't get 0, nth term says that it's going to diverge. If the terms do go to 0, that tells you nothing. Because if the terms go to 0, it could still either converge or diverge. The question is, how quickly do they go to 0? So first thing we do is look for the nth term test, because usually we can spy that real quick and see if it works. Next thing we're going to look for is, do we have one of our special types of series that are easy to identify? Geometric series, p-series, telescoping series, alternating series. These are usually quick to identify, and if they're quick to identify, you usually know exactly what you should be using to determine convergence or divergence. 3, look to use the integral test, root test, ratio test. Integral test, you would use the integral test if the series looks like it could be related to a function that is very easy to integrate. Ratio test, use that if you're working with exponential and or factorial functions. Root test, only use that if everything is raised to the nth root, or sorry, the nth power, so that we can then take the nth root. So knowing when to do each one is important. Finally, if none of that seems to be working out for you, the last thing you would try is to do a comparison test. Do either direct comparison or limit comparison, doesn't really matter, but you would do a comparison test and you would say, okay, can I compare to, say, a p-series or a geometric series? Those are the easiest ones to try and compare to, because it's very easy to know whether or not a geometric or p-series converge or diverge. So let's look at a couple of examples here to kind of round this all out. So first one here. If we follow this approach, first thing we should think of is the nth term. I think right away you look at this as n goes to infinity, and you should see what the limit's going to be. The limit is n goes to infinity of n plus 1 over 3n plus 1. You should automatically see that that's going to be a third, right? N over n, so you do 1/3 as your answer. That's not 0. Since the terms themselves don't get closer and closer to 0, they get closer and closer to a third. This thing diverges by the nth term test. Okay? Next one. Right away, you should look at this and see, it looks like geometric. This looks like the sum of a r to the n, where r is pi sixth. Pi sixth is less than 1. When the absolute value of r is less than 1, we're going to converge by geometric series test. Okay? Let's look at this next one. Root test, nth term test, not going to work. It does go to 0. Doesn't look like a special series. It's not geometric, it's not p, it's not alternating. So the next thing is, let's think about integral test. If I look at this function n e to the negative, or x e to the negative x squared, is that a function that looks like it would be fairly easy to integrate? I would say yes. Is that function positive, continuous, and also decreasing? I would say sure, it's positive because we're working with x greater than or equal to 1, right, because of the series. Is it continuous? Yes, because both of these functions are continuous. And is it decreasing? I would say yes, because really you could think of this as x over e to the x squared, because the negative exponent, we could bring this down. And the denominator is certainly going to grow much faster than the numerator, which means this thing's going to go down to 0. So sure, it's decreasing. So for all those things, I'm going to use the integral test. So I'm going to do the integral from 1 to infinity of x e to the negative x squared dx. Well, in order to do that, it's an improper integral, so I'm going to do the limit as b goes to infinity of the integral from 1 to b of x e to the negative x squared dx. I'm then going to think about how I'm going to integrate, which would be substitution. U equals negative x squared, du equals negative 2x dx. I don't have the negative 2, so I'll divide it over. And what I end up with is the limit as b goes to infinity of the integral from 1 to b of negative 1/2 e to the u du. So that's an easy integral to do. So I have the limit as b goes to infinity of negative 1/2 e to the u, which was negative x squared, between 1 and b. I'll then plug b in, I'll plug 1 in, and subtract. So what I end up with is the limit as b goes to infinity of negative 1/2 times e to the negative b squared minus e to the negative 1 squared. Well, as b goes to infinity, that's just going to stay what it is, so it's all a matter of what's going on here. So as b goes to infinity, remember this is actually in the denominator because of the negative exponent. Well, as b goes to infinity, then that tells me this is going to go to infinity in the denominator, which means this whole thing, 1 over e to the b squared, is going to go to 0. Well, if that goes to 0, what am I left with? Negative 1/2 times here, so I get 1/2 e to the negative 1. Doesn't really matter what answer I got other than the fact that I know that this is a constant. So what does that tell me? It tells me that the integral converges. And then, therefore, by integral test, the series diverges. And what you see is that some tests definitely take a lot longer to get through than others do. Some there's very little work to see that a series converges or diverges, and some there's quite a bit more. Here are two more examples. Let's look at this one here. So this one we already looked at a couple times before. It's our general harmonic. So let's say I'm going to compare to the sum of 1 over n, which I know is a harmonic series that diverges. And why am I going to do that? Because if I try to do nth term, it doesn't work. This thing goes to 0. I'm not going to say this is a p-series. It's not a geometric series. It's close to a p-series with the harmonic, but it's not quite harmonic. It's not alternating. I could use the integral test, but this limit comparison test will work a lot better. So let's do the limit as n goes to infinity of 1 over 3n plus 1 divided by 1 over n. So I take the limit of both of them, and what I'm looking to get is a finite positive value. Well, this will be the limit as n goes to infinity of flip this and multiply, so I get n over 3n plus 1, which will give me a third. That's finite positive. So then I can say, therefore, by the limit comparison test, LCT, the sum of 1 over 3n plus 1 also diverges. Let's look at this next one. This should have an n right here. So right away you should identify this as an alternating series. So I would think right away to try to do the alternating series test. In alternating series test, we only test the non-alternating piece. So I want to do the limit as n goes to infinity of 3 over 4n plus 1. I hope to get 0, and I do. Why? Because the denominator is going to go to infinity, makes the whole fraction go to 0. I'm also looking at whether 3 over 4n plus 1 is less than or equal to 3 over 4n plus 1. Remember, this is the an plus 1 term, and this is the a sub n term. So a sub n plus 1 has to be less than or equal to a sub n. Well, clearly this is going to work. I mean, the numerators are exactly the same, so it's all really about the denominators. If this denominator is bigger, then this whole fraction would be smaller. So is 4n plus 1 bigger than 4n plus 1? Well, sure it is, okay? Because this is 4n plus 5 when you multiply this out, and this is 4n plus 1. So because I'm adding 5 here and adding 1 here, certainly this is bigger. So this checks out, this checks out. So by alternating series test, the series converges. All right, take a look at this next one. Again, start thinking about your thought process. Nth term test, p-series, geometric series, alternating series. Look through some of our special tests. Is it root test, ratio test? Well, right away, I would think, as I go through all that, ratio test is a good one. Look at what type of functions are in here. Factorial, exponential. This is a prime candidate for ratio test. So a sub n is n factorial over 10 to the n. A sub n plus 1 is n plus 1 factorial over 10 to the n plus 1. So if I did the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, that would give me the limit as n goes to infinity of the absolute value of n plus 1 factorial over 10 to the n plus 1 divided by, so I'll flip and multiply since it's a fraction, 10 to the n over n factorial. We've already simplified n plus 1 factorial or n factorial a bunch of times. And this 10 to the n plus 1, 10 to the n, remember this is actually 10 to the n times 10 to the first. So if I multiply those together, the 10 to the n's will cancel, and I'll be left with a 10. So what do I have here? I have the limit as n goes to infinity of, I don't really need the absolute value because everything's positive in this case. N goes from 1 to infinity. N plus 1 factorial over n factorial would give me n plus 1 left in the numerator. I'd have a 10 left in the denominator. And as n goes to infinity, well, this numerator is going to go to infinity, sending the whole thing to infinity. Ratio test said if you get infinity for this limit, then the series diverges. So therefore, the series diverges by ratio test. Okay, one more. Seeing that this thing is raised to the nth power, this in here is not going to be like a geometric series because there's n's inside there. It's not a constant. But seeing that the whole thing's raised to the nth power right away tells me root test. So if I did the limit as n goes to infinity of the nth root of n plus 1 over 2n plus 1 to the n, this simplifies really nicely, giving me the limit as n goes to infinity of just n plus 1 over 2n plus 1. N top and bottom, so the limit should equal a half because of the coefficients. That's less than 1. Ratio test says when your limit's less than 1, what happens? series converges absolutely. So by root test, the series converges absolutely. You don't have to put that last part in, but since we have it anyway, it doesn't hurt to say that. But the series converges. Notice that in every one of these questions, we were just looking to determine whether or not the series converged or diverged. We didn't really look at what it converges to, because most of these tests we're running through don't really tell us what the series converges to. They only tell us whether or not the series will converge or will diverge. We're going to have to additionally start to look at, okay, now that we know that the series converges, we need to find out what it converges to. We're going to need to start working with that question a little bit more, and we'll do that using our next topic, which would be power series.